Thank you very much, Marion, and to Jim for the invitation to speak today and for the support of our Origins collaboration. I'm going to talk mainly about the mission that's currently happening on the surface of Mars, the Mars Science Laboratory mission using the rover Curiosity. But I'm going to start by talking about how we look for life on the early Earth, because how we look for life on the early Earth informs ways that we might improve chances for understanding the habitability of Mars. So just to make clear at the beginning, the Mars Science Laboratory mission is not a life detection mission. It's a mission to evaluate the habitability of Mars' surface. And we do that by looking at the biological potential in a particular environment, which is Gale Crater, and study the geology and geochemistry of that place, particularly focusing on the role of water and the impact of surface radiation, because surface radiation is very important for evaluating habitability. I would also add that this very exciting mission that has all sorts of opportunities for citizen science, because every image that's been taken by Curiosity is archived almost immediately on the JPL website. So people can go to that website and look at the images and see what they see. It's not what the scientists involved in the mission, what they see is one thing, but other people will see different things. And I encourage anybody who's interested in this to look at those images, because an enormous amount of the work is connected with images and interpretation of images. So if we're evaluating habitability, we need to have a starting point, and that's certain assumptions and hypotheses. And the first one would be that extraterrestrial life will resemble earthly life, because it'll be based on carbon chemistry and it will operate in an aqueous environment, because carbon's the only element we think is chemically suitable and ubiquitous and abundant in the universe. Life will process chemicals to obtain its carbon and energy. It will make copies of itself. It will be autonomous, and it will evolve in concert with its environment. We can't define life, but we can define what life does as we know it. And Mars biochemistry will operate as it does on Earth, because it will comprise physiologies that yield energy. It will have processes for replication, and it will construct its complex molecules from simple universal precursors, just as life on Earth does. I make this analogy to point out that the search for life on the early Earth and the search or the understanding Mars habitability is very difficult, very complicated, very challenging. And we know that because simply understanding the origins of humanity is a very difficult problem to address, because the fossils, the remnants of early man, are very, very rare. And we're looking at a time period for human evolution that goes back roughly 200,000 years, depending on what you call human, or modern humans anyway. The search for early life on Earth goes back 3.5 billion years, and fossils are also incredibly rare, but they're also cryptic. And there's a lot of information in a human skull. There's not so much information about early life based on a few scattered remnants of carbon preserved in a sedimentary rock. So in order to make robust statements about the antiquity of life on Earth, for example, we need multiple lines of evidence. And we call those lines of evidence biosignatures, because they come in very different types, which I'll explain in a second, as in now. So one kind of biosignature is a body fossil, like a fossil of a human skull, for example. But it could be a fossil microbe. Sometimes microbes change the textures and fabrics of rock and leave evidence in that form. That's biofilms, for example. Sometimes, photosynthetic organisms produce a lot of organic matter. So a concentration of organic matter is a signal for life. life fractionates isotopes. I'm not going to talk about it in great detail, but you can question rocks for the presence of particular fractionations that will be diagnostic of biology. And life also produces very distinctive gases that are unstable in their own right, for example, methane, dimethyl sulfide, nitrous oxide. Those gases are in our atmosphere as a consequence of the activity of microbes operating in soil and the ocean, for example. But the place that we find biosignatures is also critical to the evaluation, because the biosignature has to be within context. Something out of context doesn't mean very much. So we have no idea when life evolved on Earth because we have no records of the origin of life. Finding the earliest records of life is very difficult because all the old rocks that we have on Earth are corrupted by the effects of temperature and time, radiation, etc. They've all been metamorphosed. Early life was entirely microscopic. It had no preservable hard parts, hence the rarity of fossils. Life is everywhere now, and modern life confounds the search for early life. Life has shaped the Earth's surface in terms of its chemistry, so we can evaluate or query the chemistry of rocks for evidence of the antiquity of life. And that's much the same as what Curiosity is doing on Mars. And some of the best preserved old rocks on this planet in a place that's dear to my heart, and that's Australia, of course. And so I'm going to show you some images from particularly Western Australia where we have very old rocks preserved. The red rock in the middle of this diagram is a rock from the so-called Dresser Formation of the Pilbara Crater in Western Australia. The Pilbara Crater is up on the northwest coast, and there are sequences of rock that are really well dated. That's another important aspect of this work. The radiometric ages of these rocks are known very accurately, and of course it's no use studying a rock that you think is 3.5 billion years old if it's only 1.5. And we're talking about a very tiny slice in geological time way back here in the Archean eon, 3.5 billion years ago. So here are some images of objects that have been found in rocks in the Pilbara Craton. They go back to, I think, the 1960s and 1970s. And these were described by Bill Schopf and others. And you can see they're scraps of black stuff in rocks, in chert or in silica. You can see they're very indistinct. They're preserved in 3 dimensions, and therefore to get a picture of it, you've got to make montages, and that's very subjective how you put those together. And you need to interpret those structures in terms of what might be behind that. And here Bill has constructed a chain of cells that he thinks is represented by this object. Pardon? Yeah, 10 microns. Yeah. The rules about interpreting these kinds of objects is they must have pedigree, they must be coming from rocks that have the right ages and the right sort of environment where you might expect to find life. You should be able to find, if these are real fossils, comparably aged assemblages that look similar. They've got to belong to the rock and not obviously to do with something that's happened after the rock was deposited. And they've got to have the right sizes and shapes to be representative of biology. And of course, these more recently were challenged roughly 20 years after the original paper by a group of scientists led by Martin Brazier at Oxford, who claims that these objects are not really fossils. They're actually artifacts, basically carbon or iron minerals crystallizing around mineral grains. And so that work came under a lot of challenge. I think it's probably still under challenge. But interestingly, though, a group also involving Martin Brazier subsequently produced pictures of objects in rocks equally as old. Well, they're claiming they're slightly older, 3.5 billion years. But these objects have got the subject to the exactly same caveats. They don't look entirely convincing to me. So this is to get across the point of view that this is a really difficult topic, and there are many, many arguments for and against these things being evidence of life. But then we have objects like this. They're macroscopic, they're stromatolites, and we find them in the same places we find those very old microscopic objects. They have different forms, and most importantly, we can see modern analogues close by that have very similar kinds of shapes and textures. And stromatolites are basically formed when microbes trap and bind sediment. Microbes form sticky surfaces, and basically that's the underlying principle behind the formation of stromatolites. And we can go to a place nearby the Pilbara, Shark Bay in Western Australia, and a place called Hamlin Pool, which is a restricted basin off the Indian Ocean. And there we can see stromatolites of very different shapes and sizes. Some of them are stranded above a high water mark. Those ones people generally think of as Shark Bay stromatolites. But you look in all the subtidal areas around Hamlin Pool and you can find all sorts of weird and wonderful shapes representing different kinds of stromatolites, representing different kinds of microbial communities. So coming back to the Pilbara Craton, and we have the Dresser Formation and we have the Strelley Pool Formation, and the Strelley Pool is the most convincing. This is a very large boulder, and you can see here, you can see a coin up in one of those holes there. So this is the underside of a rock that's completely made of stromatolites, and this is the top of the rock, and you can see there very small domes, about 10 centimetres across. But this is just one type of stromatolite that we find in Strelley Pool Chert. Here's another type. This is a domal stromatolite, and it's encrusting a pebble of an older formation. And so it's evidence of the growth of these objects in shallow water on a rocky platform, because we've got the rocks that the stromatolite grew on. And to me, that's also evidence of changes in sea level at that period of time, because the rocks had to be eroded, and then the sea level had to come up, so that because these things are always deposited underwater. And Abigail Allwood, who's now at JPL, described all sorts of different morphologies of these stromatolites in the Strelley Pool Formation that correlate with water depth and therefore represent different kinds of microbial communities 3.5 billion years ago. And the different forms, the different morphologies tell us that life was complex by then, that we've basically got an ecology already established that long ago. What I do and what I'm interested in involves looking at fresh rocks, not at the surface but in the subsurface, where they have not been exposed to air, water, radiation from the surface. And for an example of this is the Agron drilling project that was completed last year, where we obtained cores through these very old sequences. We can measure the stratigraphy, and we can study these rocks for their contents of redox-sensitive trace elements, isotopic fractionation. And we can also look for organic molecules in these rocks that might tell us something about the physiology of organisms. So here's just some pictures of that drilling project, where we add traces to the drilling water to determine how much the cores were affected by the drilling fluids. The cores have been roughly put in their stratigraphic positions out in the field. Here's a picture on the left-hand side of how beautifully preserved these black rocks are. They're very pristine. There's a tremendous potential for studying antiquity of life using rocks like this. And biology has been very helpful to the organic chemists who are interested in organic molecules preserved in these rocks, because the three domains of life here produce very diagnostic lipids with very specific structures, so we can query these rocks for the presence or absence of molecules that are diagnostic for different kinds of physiologies. And this brings me to the Mars Science Laboratory mission, and the Curiosity rover, which was launched day after Thanksgiving 2011 and landed on August the 6th, 2012. It was a very exciting night from anybody who had anything to do with this mission, for anybody that actually stayed up to see it on television. Remember the 7 minutes of terror as Curiosity entered the atmosphere and landed. And as I said, you can keep up to date with this on the website of JPL. And interestingly, JPL, even though it's funded by the government, is run by Caltech. So JPL is not being shut down by the failures in Washington. The place that was selected for landing is Gale Crater. It was selected after a very intense series of debates by the scientific community. And it was selected on the basis of, first of all, the fact that they could identify safe landing spots, but also that there's a large mountain in the middle of Gale Crater that has a sequence of layered rocks. And like Earth, layered rocks tell you that you're encoding a history, that the sediments are recording what happened somehow. They're recording what happened at the time those sediments were deposited. So it's 150 kilometers in diameter, and this mountain in the middle is 5 kilometers high. It's been studied very intensively using orbital spacecraft and telescopes and spectroscopy, so they know a lot about the rocks, or not a lot, but they know at least something about the rocks in the mound. And the other interesting aspect is this area coloured in blue here, which looks like a fan that has been deposited in rocks that were weathered out of the wall of the crater. And basically, here's a diagram here. So you can see a hole. You can see holes in the wall of the crater where rock is missing, and you can see evidence of a fan outlined in purple. And we can see evidence of layered hard rock below that, and we can see clays in the bottom of the mound. But whenever you have a fan or a sedimentary sequence where rock has been moved from one place to another, you also, and if there's been standing water involved, then you will expect at the very tip of the fan you'll find fine-grained rocks. And fine-grained rocks on Earth are the places where you're most likely to find evidence of life, or evidence of habitability at least. Curiosity's payload comprises two kinds of instruments. Remote sensing instruments. There are 17 cameras on Curiosity. There are large cameras like the mast cam, two cameras up in the mast there. There's one called Marley out on the arm, which is a hand lens imager. There's a chem-cam, which is a camera that measures radiation coming from when a laser zaps a rock and makes a plasma, and the spectrum that you can get back from that plasma is diagnostic of the minerals or the elements present in the rock. They're cameras for hazard avoidance and for navigation. And there's also a camera in the base of the rover that was used to image or make a movie of the whole landing sequence. There's instruments for measuring the weather, the radiation environment, and in the body of the rover, the two main parts of the payload, which are the contact science instruments, the SAM, sample analysis on Mars, which looks at chemistry of rocks, and ChemIn, which is an X-ray instrument that determines mineralogy. So we've got to have some strategy for evaluating habitability and looking for biosignatures. And one of the things we did before the mission was launched was to make ranked lists of biosignatures and how good they are, how definitive they are, how readily they're detected using the payload. And the other strategy that's used is the science of taphonomy. And taphonomy basically is the study of windows of preservation and processes of preservation, because if you look in the right, by selecting places where fossils or biosignatures are selectively preserved, you can improve your chances that you're going to find something. So just here is a summary: organic molecules, a biosignature, Atmospheric gases can be a biosignature. Both of them can be highly definitive. So what this table is telling us is what we're supposed to be looking for and also where we're most likely to find it. One of the big achievements of this mission, I think, is the imagery. The imagery's been spectacular from day one. And in this case, we're looking at a photograph captured by an orbiting spacecraft, Mars Reconnaissance Orbiter, MRO. MRO is one of the 2 satellites orbiting Mars that that's involved in sending data back because they're large volumes of data. And MRO and another spacecraft called Odyssey are basically the vehicle for sending data to Earth. But from Earth, we can also contact Curiosity directly, but not transmit lots. We can transmit simple instructions, but not get lots of data. And MRO has basically captured Curiosity on the parachute during its descent stage. And you can see how spectacularly detailed that image is of the parachute. This is another image that was taken by the descent images. So as the heat shield was jettisoned, we've captured that. As the rover is landing and the rocket-propelled lander, as the rocket's fired, you can see the dust that's been stirred up by the rockets. And this is the image that's captured or embedded in my brain, because we were sitting at JPL during the landing sequence and everyone's getting excited. But the real proof to me that this thing had landed safely was when this image appeared up on the screen. It was just a couple of minutes after the landing. They thought the landing was successful. And basically you've got the first picture of the mound in the distance and the shadow of the rover and also the rover wheel. So you can tell there's no doubt about it safely on the ground. There's another image I like. This is after the testing the first attempts to, or the first effort to move the spacecraft, and looking back where it was, we've got evidence of the track marks. The place where Curiosity landed was called Bradbury Landing, after a well-known science fiction writer. In the distance there below the mound, you can see the scour that was made by the rockets on the lander. You can see a shadow of Curiosity here. And looking closely at the scour where the surface dust has been removed by the rockets, you can see that the evidence of the fan from a river that possibly once flowed out of the crater wall, because you've got a jumble of rocks of different types and sizes, but they're also rounded. The rockets kicked up pebbles and dust. Here's an image of the top of the rover taken with a hand imager, and you can see the specks of dust and whatnot on the top kicked up. This is the first remote sensing chemical data that came from the ChemCam. There's a rock they call Coronation, and basically it zaps the rock with a laser, generates a plasma, measures the spectrum that comes back, and gets very detailed elemental composition, and that enables inferences about the mineralogy of this rock, which is basically basalt. But then the whole surface of Mars is basalt, and that's the expected result. There's an alpha particle X-ray spectrometer. Is a different way to measure the elemental composition of rocks, and basically by using the ChemCam remotely and the APXS, which basically requires the arm to be placed very closely on the rock, they get data two types of data that's going to tell us something about the mineralogy. And the mineralogy, of course, tells geologists something about the history of those rocks, what sorts of conditions they would have been formed under. Here's a map showing the landing site, Bradbury Landing, and something about the rock types in the immediate vicinity of the landing area. These rock types had been identified prior to the landing on the basis of spectroscopy and the camera imagery, and they identified that there were 3 basic different types of rocks in the immediate vicinity of the landing. one they called hummocky, one they called cratered, and one they called fractured. And they made a decision to go to the intersection of these three units to try to understand their physical relationships to each other, which is top, which is the bottom, which might tell you more, or would certainly tell you more about the particular environment where Curiosity landed. So there was, I think, a roughly 500 metre traverse to a place called Glen Elg, during which time the rover tested out every one of its capabilities. It was a very long and involved process for the first 3 months of the landing. JPL engineers are incredibly careful, so every single capability of Curiosity had to be tested out in some kind of safe manner. Any damage to the spacecraft, of course, is going to compromise the long-term mission. And the idea is that this rover could last at least 5, maybe even 10 years. And therefore, you don't want to make a mistake in the first few weeks of the mission. And here's another image, again from MRO, showing Curiosity and its wheel tracks going away from the landing site. So I said the scour mark showed evidence of the underlying bedrock. There's some images of that. Here's a close-up of a part of that bedrock. They called it link, and you can see loose, rounded, very poorly sorted pebbles, the sort of rock that's typically deposited in a riverbed on Earth today. From the sizes and shapes of those pebbles, geologists can make inferences about how long the water flowed and what distances those rocks must have been transported in order to create such an assemblage. And here on the right, on the left-hand side, is an image of a conglomerate from a terrestrial riverbed showing very, very similar characteristics to this rock on Mars. And here's more conglomerate. So the whole area where the whole unit where Curiosity landed is basically a distal sedimentary fan caused by flowing water. Origins of that water, though, is subject to lots of discussion. Was it rain? Did it ever rain in this place? Or was this water that's come from snow, for example, snow melt? So here we have the diagram showing the alluvial fan and the ellipse, the landing ellipse that was predicted prior to the landing. And you can see there's a small cross there, which is the place where Curiosity landed pretty well close to the middle of the predicted ellipse. As I said, the imagery coming from Curiosity is I think, one of the most spectacular achievements of the mission so far. So here's some portraits taken by the camera showing the arm with the instruments at the end of the arm, the Marley camera, the drill, the APXS. Here's Curiosity's self-portrait, which was taken several months ago. And the self-portrait is comprised of 55 individual images taken with this hand lens, basically a geologist's hand lens. And basically they're stitched together and the arm itself has been photoshopped out. And what you can see down in the, I guess just here, you can see actually 4 scoops where the arm has taken scoops of rock and 2 dumps where that sediment has been basically dumped back on the ground. And that image, you might be aware, appeared as the cover of Science magazine 2 weeks ago, where there 4 of the initial papers of Curiosity's results were published. And some people have fun with this. For example, Julie Wino, I don't know if I didn't know about her until someone pointed this out. But if you go back and look at Vanity Fair, you can see many articles, short articles by this lady talking about the mission. And it's done in a humorous way, but it also makes you think, because it would have preferred to find alcohol, because alcohol is an organic molecule that's telling you something. And in fact, it's been predicted that one of the most stable small molecules that we'd expect to find on the surface of Mars is acetic acid, which is basically what you would get with ethanol and oxygen. So if they ever find acetic acid, and that's certainly feasible, there's a possibility of where it came from. This one came down just a couple of weeks ago, and it was they wanted to do a test of the hand lens capability, or just demonstrate to people that it was working exactly as planned. And this penny is glued onto the surface of the rover, and you can see how beautifully that image is preserved, as well as the dust that's accumulated on the surface since it landed. So here's another image taken again with the hand lens, part of that mosaic. And you can see the chem cam up the top. The two mask cams are the two squares, these ones here. They're two different cameras with different focal lengths. One's a telephoto, one's a wide angle. But you can see in the reflection of the chem cam, you can see Mars surface and the mound in the background if you blow that up. So. And the hand lens can even take pictures of its own bottom. Huh? Well, there's lots of aspects of these rocks that look like Australia. This is Australian desert anyway. As I said, there was instruments for remote sensing, but also instruments for contact science. And any contact between the arm and the Martian rocks involves a lot of very careful planning and testing out with a rover that's at JPL, where they can give it instructions, demonstrate that it's feasible and safe. And one of the first activities for SAM, the GCMS instrument inside the rover body, involved scooping some soil. So they identified soil here over in the distance there. You can see there's wind-blown sand deposited in the shadow of a rock. And so the rover went up to that tiny dune and pushes the wheel into the dune, demonstrates to everybody that this is wind-blown sand that's several centimetres deep and therefore safe to scoop. Here's an image from the first scoop. This is the scoop, and in fact what it does is scoops sediment and turns upside down and drops that into a shaker that then transmits it. It can send it to different parts of the instrumentation inside Curiosity. And here is the scoop itself, and with a bit of luck we'll do something. And you can see the scoop is actually vibrating as a way to sort the sediment, get rid of the large bits that won't go through the sieve, and basically concentrate the fines that are then suitable for analysis. So that one of the first movies that was taken by Curiosity's cameras. And here is the first X-ray crystallography data that came from that particular scoop of sediment, and identified on the basis of the diffraction pattern these minerals, which are typical of what you would find in basalt, as well as some other minerals, quartz, anhydrite, hematite, ilmenite, that are basically formed, well, not necessarily the quartz, but certainly the magnetite, the anhydrite, the hematite. These are formed by reactions between the minerals in the basalt and water. This is a picture of SAM, a sample analysis on Mars instrument. Looks fairly benign in its golden box. When you take the covers off, you can see it's incredibly complicated, consisting of basically ovens, heat pipes, lines, a quadrupole mass spectrometer, a gas chromatograph, and a tunable laser spectrometer. There's a simplified plumbing diagram. This is the simplified diagram. I honestly can't keep track of the valves and whatnot, but basically it allows you to put a sample in an oven and heat that up, and transfer the volatile components directly to the quadrupole mass spectrometer or to the tunable laser spectrometer up in the top left, or to the gas chromatograph that allows you to separate those molecules into individual components and then transmit them to the quadrupole mass spectrometer. So the QMS and the TLS can be used for evolved gas analysis, that is looking at gases evolved when you heat the rock. But if you find something interesting, then you can potentially separate those components and get more specific information about their identities and their isotopic compositions. So here's some typical data concerned with the EGA. So heating that particular soil, there are 4 experiments heating the same soil. The main product evolved, you can see, is water. You can see carbon dioxide and oxygen evolved, and you can also see sulfur dioxide evolved. So these are coming off from the decomposition of the minerals in that sand, but it's particularly telling that there's both oxygen and carbon dioxide present coming off at the same time, suggesting that some of the oxygen or components in the rock that are yielding the oxygen can potentially be burning any organic compounds, the things that we're really interested in detecting. That's the same diagram at the top, and some more detailed analysis of looking at specific molecules. Molecule chloromethane, which is a small organic molecule, hydrogen cyanide, hydrogen sulfide, hydrochloric acid. So it's telling us something about how complex the minerals are present in this Aeolian sediment deposit. And also evidence of small hydrocarbons based on the masses of fragments present in the evolved gas analysis. And this is now data from transmitting that material to the gas chromatograph and separating out the molecules, and we see evidence here of chloromethane, dichloromethane, and trichloromethane. So all these molecules have 1 carbon atom and different numbers of chlorine atoms. It's interesting that some of the same molecules, well, the chloromethane and dichloromethane, were previously identified in the Viking mission back in the 70s. And at that time, those molecules were attributed to terrestrial contamination that had been transported with the rover. And of course, that's a possible explanation in this case as well, because Curiosity did take some chemistry with it, chemistry to do chemical reactions on the soil, and one of the vials of those chemicals leaked, and it's possible that these things are in fact artifactual, but it's a challenge for the team now to determine whether or not these molecules are terrigenous, terrestrial, or Martian origin. And there's all sorts of ways to get at that problem, and I think ultimately we're going to be happy that these, in fact, turn out to be, a large proportion of it anyway, turns out to be Martian origin. The understanding the atmosphere of Mars is the other major part of this mission. You can tell a lot about the history of a planet by looking at the composition of gases, the gases that are present, as well as their isotopic patterns. And here is from, again by Sam, the crude composition of the atmosphere, showing what they already knew, I guess, in the sense that CO2 is the main component, roughly equal amounts of argon and nitrogen at 2%, a little bit of molecular oxygen, 0.1%, and a little bit of carbon monoxide, and there's some other trace components, and rare gases, different isotopes of argon, neon, and xenon. But what is specific or special about this data is they determine the isotopic composition of Mars CO2 quite accurately, given the constraints, at plus 44 per mil. Now, that is an isotopic composition that's rather enriched in carbon-13, the heavy isotope compared to Earth, and basically it's telling people, along with the argon isotopic composition, that Mars has lost most of its atmosphere. We don't know when it was lost, but it probably started very early in Mars history. This is the tunable laser spectrometer. Its specific job is to measure trace gases with carbon and hydrogen in them, but also determine the isotopic composition of those molecules. And one of the reasons that this was sent was because it's a very good way to detect methane. And it does this by very high resolution infrared spectroscopy. And so those of you who experience infrared, you can see wave number here, and you can see the very sharp lines that it gets for methane, but not just any old methane. You get lines for methane with a carbon 12 and 4 hydrogens, methane with a carbon 13 and 4 hydrogens, methane with 1 deuterium and carbon 12. And they give very specific lines that are measurable via the laser. And you can also measure the isotopic composition of other gases like CO2. So up here we've got the isotopic composition of the atmospheric CO2 taken several times at several different what they call sols or Martian days, an average value of 45 plus or minus 4, and the oxygen isotopic composition roughly 48. So both the carbon and oxygen are enriched in heavy isotopes consistent with loss of the atmosphere. And those values in fact quite different to values that are measured previously for Mars using the Phoenix, the Viking lander, and also Martian meteorites that have landed on Earth. So the data from Curiosity, it's very robust. The best data we have about the isotopic composition and the composition of Mars' atmosphere. And we can also get the isotopic composition of water in Mars' atmosphere. And those of you who are familiar with isotopic terminology has delta D values of 5 to 7,000 per mil. Now the standard for isotopic composition of water on the Earth is the ocean, and that's isotopic, it's 0 per mil by definition. So the water has a lot more deuterium in it than our ocean, and basically 6 to 7 times more deuterium in atmospheric water on Mars, again consistent with the loss that there was water on Mars in the past, but most of it has been lost to create such intense enrichment in deuterium and in oxygen. The reason that people were so interested in methane on Mars was because prior to launching Curiosity, there had been detections from orbiting spacecraft orbiting the Earth, as well as Earth telescopes, that suggested there were significant concentrations of methane in Mars' atmosphere. And not only that, they showed both spatial and temporal changes. Therefore, there must have been some active process generating methane on Mars and determining its distribution. And of course, those of you who, on Earth, we can form methane in several ways, but the most common way is through biology, microbes that make methane, for example, in the guts of livestock, but also microbes that live in the Earth. The other main source of methane is from fossil fuels, and again, ultimately you can say that's biological origin as well, because the organic matter that's the source of the methane is formed by life. So this question of whether there's methane in Mars' atmosphere is important to answer, because if it shows spatial and temporal changes, there must be processes producing and consuming that methane. So again, using the TLS, and this is the blow-up of the spectral region of interest by the tunable laser spectrometer, they're able to very precisely determine whether there's methane there or not, and potentially its isotopic composition. And the first measurements actually suggested there was methane present, but as they refined the measurements and pumped away the tiny bit of Florida air that leaked into Curiosity while it was sitting at the Kennedy Space Center and on top of that rocket, there was just a tiny amount of Florida air and enough methane to actually overwhelm the Martian atmosphere. But as they pumped that away, they came down to this result, which appeared in Science Express a few weeks ago, and basically they've got a detection of Mars methane about 0.6 parts per billion, plus or minus 1 or 2. So the error bars are much bigger than the measurement. In fact, it's a non-detection of methane. So Curiosity disproved results that had been produced by Earth measurements that there's methane in Mars' atmosphere.
So there is methane?
No, there's no methane. It's a non-detection. At that spot at that time, yes. And there's every intention of, there's a man from Goddard Space Flight Center. There's every intention of continuing to make that measurement, particularly through the changes in season, because if there was methane there and it was trapped in ices, for example, it's possible that as those come and go, wax and wane during Mars changes in season, that they may find something. So this is an interesting diagram. This is pressure measurements on the surface of Mars in Gale Crater on 2 different sols, Sol 31 and 93. And when Curiosity landed, it was springtime, and they went to the summer. And of course, the volatiles that are frozen in the poles evaporate to a degree during the summer, and you can see an increase, very slight increase in atmospheric pressure. Interestingly, now we have the pressure measurement basically in blue, and radiation measurement from cosmic radiation, and you can see as the pressure decreases, the radiation increases, so they're exactly juxtaposed. So the radiation environment on Mars changes diurnally. So as I said, at the end of a stream bed, if that stream flows into a lake, you will get fine-grained sediments. And was predicted, based on orbital data and also the initial results, that they might find these fine-grained sediments in the place where the 3 different rock types intersected. And this place was named Yellowknife Bay. Many of the names that are being used for places and rocks come from northwest Canada. It's a place that was explored for early life on Earth many years ago. And John Grossinger, who's the principal scientist, also had a long history of studying rocks in Northwest Territories of Canada, hence the use of names that basically reflect that history. And so here's the transect from the landing site to Yellowknife Bay, and the different rocks that it intersected at as they passed them. Found very interesting rocks like this one they call shaler. It was very fine-grained sediments with also little nodules. The fine-grained sediments indicated rock or these minerals deposited by sediment transport, and probably aqueous transport as opposed to aeolian transport. And some more images. The rock on the top, this long rock, they christened the snake. And basically it shows that the bedrock that's investigated here has been fractured by some processes in the past, and minerals have come in and filled those fractures. So fracture filling. This was the test of the dust removal tool, which is basically a wire brush, scraping away all the surfaces of Mars rocks coated with this fine-grained dust. It's basically universal signature of Mars. The stuff has probably been going around the planet for a couple of billion years. And if you want to understand the underlying chemistry, you've got to get rid of that stuff. And one way is brushing. And looking at that particular sediment, here's a image taken from the ChemCam, and you can see you've got fine-grained sediment with the basaltic composition, but you can see those white veins going across the rock. That's a calcium sulfate mineral, gypsum or anhydrite, and that's evidence again that this rock was in contact with water for sufficient time for those minerals to crystallize in the cracks. This is the first test of the drill that's used to get below the surface of particular sediments. You can see there's white rock or white material, which is a fracture. And for this particular test, all they did was put the drill onto the surface of the rock and vibrated it slightly. And that tells them straight away it's a very, very soft rock, the fact that you can just vibrate the drill and makes a big hole. Here's the first hole. It was first, the one on the far left-hand side was basically half a hole. The other one is the hole that went to the maximum depth of the drill. As the drill turns, the sediment is circulated up and into the scoop and then into the inside instruments. But they also measure chemistry using the ChemCam, so these are the laser shots. Here, 10 laser shots across the sediment. The other interesting thing about this sediment is grey. When you look at the surface of Mars, it's red, oxidized. So grey is telling you that it's minerals that have not been oxidized. So again, telling us something about the prior history of these minerals. And this one, if you watch this, these are 3 shots on 3 different soles of those 2 drill holes. And you can see from this that Mars is a dynamic environment, because you can see the laser shots and they go blurry and then they disappear because the wind has been moving sediment that came out of the drill holes, and basically you can see the sediment pile has been moving to the right-hand side of the image. So it looks like it's a slow place, but in fact Mars' surface is very dynamic. So here is more evolved gas analysis data from that particular rock, and again a lot of water, but you notice at a very different temperature profile of the water coming off. Again, the oxygen and the carbon dioxide coming off here together, and then 2 peaks of sulfur dioxide. And this evidence that there are different forms of sulfur present in this rock. And when you've got different forms of sulfur, on Earth microbes can use those forms of sulfur in redox reaction and gain energy. So this is evidence that the presence of different sulfur minerals with potentially different oxidation states is at least one kind of what's the word I'm looking for? Chemical disequilibrium that could be exploited by microbes. And the other really interesting aspect of the rock that came from the X-ray powder diffraction pattern is on the left-hand side you can see additional lines. So this is the aeolian dust. This bright spot here comes from the material that the sediment is encased in when they take the X-ray, but you can see there's a broad, bright area where I've put phyllosilicate, and so there's spectral signature of phyllosilicates, again requiring that these minerals had extended contact with water to form those clays. And so put all that together and we have evidence of an ancient habitable environment at Yellowknife Bay, because the regional geology and the presence of fine-grained rocks said the site was at the end of an ancient river system and almost certainly intermittently in contact with wet lake bed. The mineralogy indicates sustained interaction with liquid water, and also the form of the minerals present suggests that the pH was near neutral, and it was not a highly saline environment. The calcium sulfate minerals tell us something about that. The key chemical ingredients for life are present in that environment, because we've got evidence of carbon, hydrogen, oxygen, phosphorus and sulfur. And the presence of minerals of various oxidation states is evidence of a potential source of energy for primitive microbes that may have lived there once. So in terms of mission success, if they had made MSL a life detection mission that didn't detect life, then people would say, oh, it's a failure. But the search for habitability, that's something that you can say yes to no to. Whatever you find, you're still meeting the guidelines for mission success. And I think that I think it may be better to answer that question a little bit later, because there's still a bit to go through. And So the ultimate destination is Mount Sharp because this is extensive layers of rock. And prior to the launch, it was hypothesized that these layers of rock will encode the history of Mars with respect to both activity of water and oxidation state. And the idea is that a warm, wet Mars would produce clays. They're shown in this stratigraphic chart here is the green. Then as Mars dries out, you will get evaporite minerals like sulfates. That's the orange in this stratigraphic chart, I think. Oh, sorry, the blue. And on top of the blue, perhaps iron oxides, which are known to be the sorts of minerals that are accumulating in Mars' surface at the present time. So evidence that conditions through the life of the planet have changed, and therefore by really detailed analysis of these sediments we might learn more about the changes themselves, but also the timescales of those changes. So here we have the landing site on the top left, the Glen Elg, which was like the 500-metre traverse, and you can see now it's quite a number of kilometres to the base of Mount Sharp where they've identified a potential way through sand dunes to get to the lower reaches of Mount Sharp where spectroscopy tells us there's an accumulation of clay minerals. The rover does something like 100 metres per day. They're hoping to increase the rate of transit and to get to the base of Mount Sharp by the middle of next year, doing minimal contact science along the way. And here is position of rover at Sol 354, which is a few weeks ago, July the 4th. So it's basically past the landing site and well on its way to the base of Mount Sharp. Mount Sharp is shown here. So Curiosity has to transit a series of sand dunes. There's all sorts of interesting geological potential within these basal sediments. You can see the layering of the rocks as you go up the mound, shown even more dramatically here. There's a large boulder up there, that's actually the size of Curiosity. So it's hoped that sort of by this time next year, Curiosity will have gained a significant amount of information about those particular sediments. The investigation involves incredible engineering from JPL. The fact that this rover, the size of a car, was landed safely on the planet, the fact that just about every single thing on the rover is working as planned, in fact, in many cases better than predicted. There's a very large engineering team. These are the names of the people on the SAM science team, which is where I was selected as a participating scientist. And the other thing I would like to say is that the leadership of this particular project has been spectacular by John Grotzing of Caltech, but also Joy Crisp and Ashwin Vasaveda, who assist John in managing the project, and something like 450 investigators agreeing mostly on strategy. They don't agree on interpretation of what they're finding. That's really good because there's lots of very good scientific debate going on during team meetings, but at least the team can agree on the strategies that drive Curiosity and drive the science that they do. And I think I should leave it there, and thank you for your attention. I'd be pleased to answer questions if you have them.